In this lecture, we will see Fourier series, which is one type of the choice of eigenfunctions that we studied in the Fourier analysis lecture previously. So remember, earlier we ended up with one question, how to find the inner product when you have infinite energy for the phasors, and how to choose how many number of phasors to employ in order to compute the decomposition set of t equal to some ai times xi of t. So these are phasors, okay, and this is some arbitrary signal, and we computed this ai as nothing but a coefficient which you can express something like this. In other words, for our signal, what is this? The inner product here is z of t multiplied with x star of t dt divided by x of t x star of t dt. So we know how to compute the coefficients, we know how to express this decomposition. Only thing we are still stuck with is to find out what happens here when this energy is infinite and how many I should we choose here. Okay, let's try and find a solution for these two questions. Okay, we already said that we are going to look into phasors, which means we are going to look into signals of the form e power j omega t, where the omega changes. Now, what if we choose only harmonics of a frequency? So this is trying to answer the first question. We already saw that Gibbs phenomena forces us to use infinitely many frequencies, but infinitely many how? Should we choose integers or should we choose real numbers? So what if we choose integers? So in this case, we are choosing integers, meaning we are choosing phasors of the form e power j k omega t. What is that k omega t? It means that you fix a particular omega. Let us say I will fix it as 3 radians per hertz, and then I will consider all possible integral multiples of that. Plus 3 minus 3 plus 6 minus 6 plus 9 minus 9 plus 12 minus 12 and so on. So if I consider all possible integral multiples of this, once again I get infinite frequencies. Okay, so somehow Gibbs phenomena could be taken care of this because we have infinite frequencies here. So these are all what are known as harmonics. So now what if we use this infinite set of phasors? Okay, now we have infinite set of eigenfunctions which are orthogonal to one another. Remember, they are all orthogonal, we can show that, we have already shown that. If we use this set to represent any z of t, okay, that is, I am going to say that this k is going to be from minus infinity to plus infinity some ai times e power j k omega t. Then what all kinds of signal can this set of eigenfunctions represent? First thing is, these are all periodic signals and their frequencies are of the form k omega, okay, which is harmonics of one another. So remember, when we add periodic signals together, the resultant is also a periodic signal and the period is the least common multiple. Of course, here they have to be periodic because we are adding only integral multiples, and the ratio of the period is always a rational number here. So for that reason, we are ensured that the sum here is also going to be a periodic signal. So z of t has to be periodic, and not only periodic, it has to have a period which is the least common multiple of all these components. So which means if we have a period t and the other signals will have a period t by 2, t by 3 and so on, then the least common multiple of all these signals that we have here is capital T itself. Okay, and what happens to the frequency? The frequency is the greatest common divisor. So how many ever frequencies that we can use to represent this, the greatest common divisor is what we'll denote as the frequency of z of t. So what this tells us is z of t has to be a periodic signal, and then it should not only be that, but its period should be least common multiple of these components. Not only that, but we also put a restriction on the period and the frequency itself. Now let's say if my period of the signals are going to be t by 2, t by 3 and so on, I cannot have a signal z of t which has a period which is greater than capital T. So I cannot have a signal which has a period which is, let's say, 2t or 3t and so on. So there is a restriction on the period. In other words, there is a restriction on the frequency itself. So if there is a limit on the maximum period, then there is a limit on the minimum frequency, right? So in other words, we can represent signals only which are multiples of capital T, that is t by 2, t by 3, t by 4 and so on, which means we can represent frequencies only of the form omega 2, omega 3, omega and so on. So the restriction that is introduced by this choice of eigenfunctions is that the signal z of t has to be periodic. Not only that, it should have a frequency which is an integral multiple of the fundamental frequency in the harmonic. So this omega is the fundamental frequency. So if we have a set of periodic signals, for example, all our AC signals that are coming from, let's say, our power station, they are all sinusoids, okay, or there are some components or some linear combinations of sinusoids. So we know that they are all periodic and they will have certain frequencies, right? So if we want to represent only a set of signals which we know for sure are periodic, and we know that their frequencies are going to be integral multiple of some fundamental frequency, then we can use this choice of eigenfunctions. Of course, if you use this choice of eigenfunctions, you cannot represent an aperiodic signal. For example, if you have a signal which is like this, right, and it does not repeat at all, this is an aperiodic signal. You cannot represent this signal using this choice of eigenfunctions. But if you can convert that into a periodic signal, then you can represent that, okay. So representing a set of periodic signals which have a fundamental frequency omega through this choice of harmonics or harmonic phasors is what we would call as the Fourier series. Okay. Now only thing that is now left is how do we find out this AI? Okay, so we figured out a choice, or we started out with one particular choice and we found out that this choice of eigenfunctions is now going to help us represent any periodic signal of some fundamental frequency. First problem, we somehow found a choice. Of course, there will be other choices we will see later. So this is like case 1. So we have one case where we have chosen a set of frequencies which are harmonics, which are orthogonal eigenfunctions, and we have found out the signals which can be represented using this. Still one more thing we are yet to answer here. How are we taking care of this inner product problem? It has energy infinity, right? Let's see how are we taking care of that. The interesting thing that we have done in choosing the harmonics or in choosing the eigenfunctions is that we have restricted ourselves to periodic signals, and periodic signals of period t, t by 2, t by 3 and t by 4 and so on, which means any signal that you pick from this set, there are infinitely many phasors, any that you pick will repeat after t seconds, because the period, the maximum period is t, after that it is t by 2, t by 3 and so on. In other words, if the maximum period is t, anything that you pick now will have multiple cycles in that. So all will be periodic in capital T. So if something is periodic in t by 3, it means it will also be periodic in t. If something is periodic in t by k, it will also be periodic in t. So this is a property that we are going to exploit to take care of this infinite energy problem. What are we going to do? We are going to focus only on one period, because the entire signal is anyway going to repeat after the period t. So why bother about what is a repetition? Just focus on something which is not a repetition. We can anyway copy paste whatever is happening outside. So this is how we are going to overcome the problem of infinite energy. We focus ourselves on a finite duration signal, and the duration is this capital T, which is given by the fundamental frequency. So basically we will take the period of the fundamental component of all the harmonics that is present and then focus only in that period. So remember, we already discussed when we talked about energy signals, any finite duration signal will have finite energy, which means if you compute the inner product of the phasor in the interval minus t by 2 to plus t by 2, we have to take a period which is of length capital T. So it can be between 0 and t, or it can be between minus t by 2 to t by 2, or it can be between 2t to 3t. It doesn't really matter. It can be any interval. You will get the same result for all these intervals. Whichever interval makes your integration easier, you can pick that interval. So for convention, we will choose from minus t to plus t, minus t by 2 to plus t by 2. So if you compute this for phasors, what do you get? So you get, let's say, e power j omega t r phasor. Multiply that with e power minus j omega t, which is its conjugate. Okay. What is this? This is simply nothing but 1 dt from minus t by 2 to plus t by 2. So no matter what the period is, where you start or end, as long as the period duration is capital T, this integral will always give you capital T for the phasors. So when you choose your phasors to be harmonics of fundamental frequency, the inner product is now going to be computed within a finite duration, and that duration is the fundamental period, and in that period the inner product is always capital T. So we have solved both the problems. We now have a choice, and that choice is simply nothing but the set of all harmonics, k is minus infinity to infinity, okay, given a particular fundamental frequency omega. If omega is 1, then we have frequencies plus or minus 1, plus or minus 2, plus or minus 3, and so on. If omega is 3, then we have plus or minus 3, plus or minus 6, plus or minus 9, and so on. So given a particular fundamental frequency, you can construct this entire set of the orthogonal eigenfunctions, which are the basis from which will represent any periodic signal of fundamental frequency omega. Alright, and how are we going to find the corresponding coefficients? We are going to find the corresponding coefficients using the inner product, because the inner product now does not have the problem of infinity, because we made sure that we are looking only into the finite duration. We will focus only on the finite duration, and everything that is happening in one period is exactly what that will happen in other periods also, because it is periodic. You can simply copy paste things. So whatever integral that you compute here is exactly going to be the integral when you compute from t by 2, 3t by 2, and so on, right? So we just focus on one period to compute this inner product, which means we can find out the coefficient ai. Let's put all of what we saw together. So we'll take any signal z of t, okay, which has a fundamental frequency. And remember, what is the fundamental frequency? Given some omega, the fundamental frequency we can represent any z of t which is periodic and has a period capital T. Of course, if it has a period capital T, it will also have a period which is equal to 2t, 3t, and so on. And such signals could be represented using our eigenfunctions. So how did we choose these eigenfunctions? The eigenfunctions are nothing but they are phasors, and they are not only just phasors, they are harmonics of one another. And how do we find these coefficients? We are finding these coefficients by focusing ourselves only on a finite duration which is equal to the fundamental period. So remember, what was the inner product? It was something of this form, and in this case it is integral z of t with x I conjugate divided by and we already saw that this is equal to capital T, which means this coefficient is nothing but 1 by t integral z of t. You have to take the conjugate of these phasors. The conjugate of this phasor is e power minus j omega kt dt. That is exactly what we have here. This is called Fourier series. So we have a series here, right? So basically what we have done is we have represented any periodic signal in terms of a series, okay? And the coefficients of this series is computed through this equation. And this computation is what we refer to as Fourier series representation. So let's see an example, okay? So let's say we want to represent a rectangular signal or a square signal in terms of it's a Fourier series decomposition. In other words, let's say we have something like this. Of course, it has to be periodic, only then we can compute the Fourier series. That's the current choice of eigenfunctions, okay? So let us assume that it is periodic with some period capital T. Otherwise, this is minus t by 2 to plus t by 2. Let us say this is minus t by 4, this is plus t by 4, and this is, let's say, 1. Now, if we want to compute the Fourier series of this signal, so how do we find the Fourier series? Let's call this as z of t. So we said that z of t is equal to summation k running from minus infinity to infinity ai e power j k omega t, okay? And what is omega here? In this case, omega is 2 pi by t, right? So we can simply replace this as 2 pi small t by capital T. Okay, now the question is, how do we find these coefficients? The coefficients are basically the Fourier series coefficients, and we know that we can find this as 1 by t integral minus t by 2 to plus t by 2 z of t multiplied with e power minus j k 2 pi t by t dt. Okay, how does z of t look like in this interval? In this interval, it is 1 from minus t by 4 to plus t by 4 and 0 everywhere else. So all we need to do is just integrate in this interval. So we get e power j k 2 pi t by t and minus j k 2 pi divided by t from minus t by 4 to plus t by 4. This gets cancelled. So we have 1 by pi k e power minus j k 2 pi capital T by 4t minus plus e power minus j k 2 pi minus t by 4t. In other words, this is 1 by pi k e power j pi k by 2 minus e power minus j pi k by 2 by 2j. This is nothing but sine k pi by 2 divided by, so remember here k is 0 plus or minus 1 plus or minus 2 and so on, which means a 1 is nothing but, just substitute k is equal to 1 in this. So if you substitute k is equal to 1, you just simply get sine pi by 2 by pi, which is nothing but 1 by pi. A2 is, once again, so just simply substitute sine 2 pi by 2 by pi k, which is 0. A3, which is 3 pi by 2 by pi k, which is nothing but minus 1 by 3 pi, and so on. So you can compute a plus or minus 1 plus or minus 2 plus or minus 3 like this. But what about a0? How do you compute a0? a0 is limit k tends to 0 sine k pi by 2 divided by pi k. So you have to take the limit. In this case, if you directly just substitute k equal to 0, you will get 0 by 0 form. So you'll have to apply L'Hopital. If you apply L'Hopital in the numerator, you will get cos k pi by 2 divided by pi by 2, and in the denominator you will get simply pi. Okay, you have to differentiate with respect to k because that's the one that is tending to 0. Cancelling out, you just simply get half. Okay, so effectively we have found out the Fourier series coefficients. The Fourier series coefficients are a0 is equal to half, and a plus or minus 1 is 1 by pi, a plus or minus 3 is 1 minus 1 by 3 pi, and so on. All the even values are 0 here. Okay, only odd values exist, and we can say that in general ak is given by sine k pi by 2 divided by pi k.